Hello, I'm going to do another chalkboard video. Now, this is going to be a series of videos about what makes peak power. And today's video, I'm going to talk about air is horsepower. So, most everything, just to let you know that I get and that I'm talking about, came straight out of the Superflow FlowBench manual. Now, other than the stuff on how to run a FlowBench, which is in here, there's a bunch of stuff about why engines work and how engines work and references to papers that people have done about how engines work. Now, you can download this from the Superflow website. It doesn't really matter which bench you get because you're not really after how the bench works. It's more about the extra information, and it's something you might consider, and also if you need to reference what I'm doing. So, like I said, in today's video, I'm going to talk about air is horsepower. Now, when we talk about this, it's naturally aspirated motor that I'm going to be discussing. We all know that adding boost will add power. Well, adding boost adds more air by increasing the air density and adds power. Just as oxygenated fuels do, nitrous oxide does, it's all about how much O2 you can get into the cylinder. That's really what horsepower is about. It's not about the fuel. You can add as much fuel as you need to get the ratio correct. It's really about how much oxygen you can get into the cylinder to actually burn. Now, in this whole discussion, I'm going to just talk about naturally aspirated motors. We don't need to get into how you can add extra oxygen beyond that. We can do that in a future video if we want. So anyway, the main component that is controlling how much air is going into a cylinder is, of course, the cylinder head. And we usually get flow numbers, and these flow numbers are at, or better be at, 28 inches of vacuum. That's the industry standard, and that's really what everybody is supposed to be using so that we can compare every flow number to another flow number. Now, one of the first things you want to look at when you're looking at a cylinder head and you're looking at flow numbers is what the flow numbers look like. Now, this is a AFR 195 as cast head 202 small block Chevy cylinder head. I chose this for a later video because this was also tested independently. It's not an AFR number. This is numbers that Eric Weingartner did, and you can go to his YouTube channel and see what he's done on some of this and using this head. So that gives you a bit of a more real world to look at, which we'll also talk about later. So when you're first looking at the cylinder flow head, the cylinder flow in the head, you are looking at the numbers in CFM. Now he tested all 8 cylinders, and of course because it's as cast, it's just a casting, it's not refined, it's not been ported, they vary a little bit. I just chose, I think this was cylinder 7, I just kind of chose one at random. So if you look at it, one of the things you'll notice is the numbers start fluctuating up here at the really high lifts. And that tells you that the port's starting to get unstable. And that's not a good thing. That's actually one of the things that a porter fixes when he's working on a head. Is not always about flow numbers, but about making sure that it's a very stable port, because you need that in order to really make power. Now, air is power, but you can't just go to a huge port. I mean, if it was, it'd be easy. We could just hog them out to a monster port and make groups of power, but it doesn't work that way. So when you're looking at these numbers, one of the things you want to decide is where that CFM is kind of peaking out, or starting to do what's called backing up. The numbers start going down. That's an indication that that's where the port's starting to get unhappy. So in this case, this is around, 600-700 lift that the port is starting to have troubles. And in this one. Now I took kind of an average, and if we call it, like 650, 680 lift, we're talking like 265 CFM average across all the ports he tested. So if that's what we do, and we look at a flow, then I can say that that port is good for 551 horsepower. So how did I get to that number? Well, Superflow, who made the book, makes the manual, makes dynos, also makes flow benches, did a bunch of testing years ago in order to equate what you see on the flow bench with what you get on the dyno. And they came up with a number, and that's 0.26 horsepower per CFM. And that lets you port ahead and get some idea of where you're going to be sitting on horsepower, and that's all in the book. And so if we take, that's per cylinder. So if we're dealing with a V8 motor, you basically have that times 8. So you've got 2.8 horsepower per CFM. So if you're looking at a single runner and you're looking at the CFM, you can just multiply it times 2.08, and that will give you the basic horsepower of what the head is capable of supporting at that lift that you're looking at. Now remember, if you change the lift, you change the flow. If we were to back up here to 500 lift, you say you're running a little RV cam with this head, it's only 500 lift, short duration. So you're down here at 253. Well, you're going to wind up making less horsepower because you're losing CFM. That's why you try and find how much CFM the head is really capable of supporting, and you have to make a decision as to how much lift you can actually deal with the particular motor that you're building. Not everybody can build a 1-inch lift, camshaft motor with a big spring. So you got to kind of look at the numbers and make some decisions and see where you're sitting here. And then it's as simple as taking the 2.08 times the CFM to get the horsepower that you're going to have the potential of making. And that will give you the basic of what the motor's going to do. Now, that's good for a lot of you. Now, that number, a lot of you might say, well, I've done that. That doesn't quite work. And you're right, it doesn't quite work. That gets you to about 80% of where the engine's going to be. So for a lot of guys, that is a good enough number to see if they're in the ballpark of what they're talking about. Do I need to find a head that flows better? Do I need to port the head and see if we can get a little more CFM because I'm going to come up short? Like I said, that number is only 80%. There's another piece of the puzzle which I'm going to discuss in the next video. And that's how the camshaft affects the flow number. And so that video is going to be called Inertia Ram Principle. And again, that's also straight out of the book. So that's a little more involved, and I wanted to touch base on this first. If you're looking at a little motor, I mean, when you're looking at camshafts, the first thing you're looking at is really flow and lift to see where you're going to be to get what you want out of the motor. If you're talking a little itty bitty cam that's only 450 lift, you're going to be way down here, and that's going to affect your power. You might want to rethink that, go to maybe a 1.6 rocker and get it up to 500 lift, or you might want to go with a a short duration but a little more lift in like a roller cam and get you up into a number that's going to be more acceptable for what you're trying to do. And when you start looking at it that way, you start realizing why certain things make more power, and some of it is strictly CFM and the lift of the camshaft. And that's the basics, and that's where you start. And that's what this is. Because as much air as you can get in the cylinder is really going to control how much horsepower the engine makes. And so I wanted to start with that little bit. And I know this video isn't going to be very long. The next one will be a little more complicated. But I wanted to say that that's really where you start. That 2.08 horsepower per CFM for a V8. You can recalculate this. If you're doing a 4-cylinder, 0.26 times 4, but the airflow potential of the head is really your upper limit. That's going to be what you can make. And so that's an important number. And the quality of the flow is important. Like I said, you can't just hog it out, get a big number and say, hey, I'm going to make lots of power. That's not how it works. It needs to be a very high quality flow. The better quality of the flow, the better the motor's going to run. And that's where sometimes this gets a little wonky in what number, and it didn't quite live up to what it is because on a flow bench, you can actually see stuff. We don't talk about flow quality a lot, about where it starts to fluctuate. It starts making sounds, numbers start backing up, which people have talked about. The numbers back up, that's a bad sign. But the quality of flow is important because if it's unstable in a rapid moving motor, it's going to become even more unstable and you can't hit that flow number and your power will be less than what you think it's going to be. So that's one thing to really look at, and one of the reasons why head porters get a bench and actually test heads to make sure what they're doing is correct and to be able to see how stable that port is. The difference between an okay head port and a good head port is not really the number. It's about the quality of the flow. It's super smooth, it's super nice. And that's what head porting really gains you. And this ass cast really shows that. That's part of the reason I like this, is because you can see it starts getting a little unstable down here at high lifts, which you kind of expect. And the fact that if you look at all the numbers, and like I said, he's posted a video on this, flowing this particular head, so you can look at all 8 numbers if you want. You can see there's a variation from port to port. And that's some of what gets fixed when you actually port heads, is to equalize out everything and stabilize the port. It's not always that he can get a way more CFM out of it, which would be nice because air is horsepower. So if you can get some more CFM in there, you'll get a little more power. Now the other thing to touch about on CFM is CFM as compared to cubic inch on the motor is RPM. As you increase CFM and you leave your cubic inch the same on the motor, say you're dealing with just a 350 instead of a 383 or a 400, well then the RPM is going to be higher, because as you go up in CFM, then the RPM will move up. As you go up in CID, cubic inch displacement, the RPM comes down. So sometimes you'll start seeing why guys like maybe the 383 or a 400 small block, or I think this one was this was a 406 small block. So you start seeing why they kind of like that, because as you push the CFM up, the RPM could get beyond where you're really trying to work, and it's not as helpful. And that's another reason you can't necessarily just add hoops of CFM, because it's quality of airflow, like I said, which affects airspeed. And we'll talk about airspeed in another video. And so all of these things work together in order to come up with that peak number. But most of you just want a really general idea. So I'm going to try and simplify the basic process and the big players. And CFM is the first big player as to what makes that power. And like I said, this gets you a rough number. It's 80%. It's 80% of what you're there. You could be plus or minus either side of that. And we'll talk about that in the next video. But remember, air is horsepower and CFM matters. So first thing you're looking at, CFM versus the lift of the can and where that's going to put you. So I wish you luck on all of your projects, and I'm going to move on to the next video, and we're going to talk about inertia ramp. That's really how motors work. So see you in the next video.